Hello, everybody, and welcome to our work energy power unit. So today we are going to start by looking at work. So before we start talking about work, I want to talk a little bit about energy, because energy is the ability to do work. And once we look into work a little bit, we will be diving into energy as well. But we'll start today with work. So work is either the change in energy, or you can think of the definition as the product of a force times distance. So this is going to give us two different formulas. The first one is work is equal to change in energy. It's actually the work energy theorem, and we will get a little bit into that later on. The one I really want to focus on is work is equal to force times distance, which is awesome. Or force times displacement, actually. Let's do that. I mean, distance is the same thing because we'll probably be moving in the same direction the whole time. So our distance covered is going to be our displacement. But it's important because if we have a vector times a vector, that makes work a scalar. So both energy and work are scalars and are measured in joules. Joules, which is a capital J. So work is equal to force times displacement. That means if we look at this situation here, situation number one, situation number two. In situation number one, a box is being lifted. There's no person. I can put a person there, but I don't really know how to draw a person bending down to pick up a box. That's pretty good, actually. A person is picking up a box to a certain height, so they are applying a force over a distance. Work is done. Work is being done. In situation two, the person is just going to hold the box there, and they're not going to move. So we know that holding a weight is using energy, but you can kind of think of it like the work isn't being done on the weight, it's being done on the muscles to hold it. So in this case, if we're looking at the work done on the box, because it's not moving, no displacement, no distance, no work is done on the box. Let's add that there. So basically, no distance moved, no work. So here we go. Let's get into some problems. If I were to lift a 30 kilogram weight off of the ground to a height of 1.5 meters, how much work would be done on the weight? Well, let's draw our free body diagram. We know that I'm going to apply a force to move that up, and I'm countering gravity. I know that work is equal to force times displacement, or force times distance. So we know that our displacement is 1.5 meters. The force in this case, actually, I better erase that. The force, because we are trying to counteract force of gravity, the force applied has to equal the force of gravity. Therefore, we can use, to figure out the work being done, we can use force of gravity, which we know to be mg. So work is equal to 30 multiplied by 9.81 multiplied by 1.5, and that gives us the answer key I'm using uses 9.8, not 9.81. So let's see how much of a difference it makes before I just write down the wrong number. 441.5 joules. So we gain a joule and a half. So that does make a bit of a difference. There we go. So we are doing work against gravity, so we have to apply the same force in order to lift that box. Hopefully that makes sense. A 10-kilogram pumpkin is moved horizontally 5 meters at a constant velocity across a level floor using a horizontal force of 3 newtons. How much work is being done on the pumpkin? Okay, well, this is our square pumpkin. We can give it a little, oh, that's too thick. We can give it a little, there we go. Now it looks more like a pumpkin. We know that we have force of gravity and normal force. Those ones aren't too important because they will cancel each other out. We have an applied force of 3 newtons, and we have force of friction. If it's moving at a constant velocity, we know that force of friction is also going to be 3 newtons. So our work is equal to force times displacement. In this case, if we're looking at work done on the pumpkin or the work that we're doing on the pumpkin, we will use our applied force. So 3 multiplied by 5, and that work is going to be 15 joules. So in this case, we are using applied force, not net force, because we're looking at the work that we're doing on the pumpkin. So the work is the force we're applying. Does that make sense? Yeah, I don't really know what else to say. Question, example 3. A 3-kilogram pineapple is held 1.2 meters above the ground. How much work is being done on the pineapple? All right, so we've got a pineapple. They're kind of spiky, are they not? Pineapple, it's being held. That's a weird person. Give them longer legs, maybe, and maybe a bigger head. It's being held 1.2 meters above the ground. Work is equal to force times distance, or displacement. In this case, the pineapple isn't moving over a displacement, it's being held there. So, no displacement, no work. Hopefully that makes sense. So work is actually 0 joules. No distance moved equals no work. Okay, let's dive into a trickier one. A 1,385 kilogram car traveling at 61 kilometers an hour is brought to a stop while skidding 42 meters. What is the work done on the car by the frictional forces? So if we have our car, we know we have a force of gravity and we have a normal force. And this car is coming to a stop. So let's say it's moving in that direction, but it's coming to a stop. It's skidding, it's locked its tires up, so the only force acting is the force of friction. So we can say that, well, let's work it backwards. We know work is force times distance. In this case, we're looking at force of friction, right? We're trying to find the work done by the force of friction. And in this case, we don't know much to figure out the force of friction. We don't know the coefficient of friction. So there's another way we can do it. We can use our F net. Let's move this over. F net is equal to mass times acceleration, because we know that F net is going to be negative force of friction is equal to mass times acceleration. So we have mass, but we need to find acceleration in order to find force of friction. All right, so we have the mass of the car. We know how fast it's traveling. We know its V initial is 61 kilometers per hour. We know its V final will be 0 meters per second. And we know it's doing that over a displacement of 42 meters. So we can use kinematics to find the acceleration. The first thing I'm going to do is divide by 3.6 so that I get a new initial velocity of 16.9 meters per second. So we can use the formula Vf squared is equal to Vi squared plus 2AD. And we are trying to solve for A. So Vf squared minus Vi squared all over 2D will equal A. That is your formula manipulation using algebra. I'm not going to go through it. So now we can say that the acceleration is equal to V final was 0 minus the initial was 16.9 meters per second divided by 2 multiplied by the distance, which was 42. And that is going to give us an acceleration of, well, I'll just calculate it. I can't really read this answer key. 16.9 squared divided by 2 times 42. That is going to give us an acceleration of negative 3.4 meters per second squared. And it's negative because we're slowing down. We're going in the opposite direction of our velocity, which we established as positive. So now we can plug that in up here. So now we know our negative force of friction is going to equal mass, which was 1,385 multiplied by negative 3.4. So we know negative force of friction is going to equal 1,385 multiplied by negative 3.4, negative 4,709 newtons. So if negative force of friction is equal to negative that, then force of friction is equal to, there we go. So now we can do work is equal to force of friction multiplied by distance. So work is equal to 4,709 multiplied by 42. And we get that to be 197,778 joules. We can also write that as 1.98 times 10 to the 4. 4? 1, 2, 3, 4, 5. Haha, I knew I did something wrong. 5 joules. That's a bit of a long one, but it's got a little bit of kinematics. It's got some dynamics, and it's got some work. So that's a good one. All right, don't forget to, or thank you for watching. Don't forget to like and subscribe.